So good afternoon, everybody. I'm Felipe Moreno. I will present our work titled "What Makes a Place Feel Safe?" Analyze street view images to identify relevant visual elements. So let's start with our motivation. What if I ask to you which one looks safer between these two images? The first one on the right side are an image taken from the city center. As you can see, it's very crowded. There is a lot of movement, cars, people, etc. And in the other hand, the left one are isolated street with bricks walls, maybe some garbage, and inconclusive constructions. So I guess as I mean, in my own perspective, I will choose the right one as the most safer. So based on this, our motivation is to understand how people perceive and experience the cities. For this, we can create complex models to analyze the perception and obtain insights from inference. Our context is that urban perception is shaped by a complex landscape or design such as physical design, architecture, landmarks, and we can analyze the visual characteristics or visual appearance that define a city's identity. So for this study, we use the Place Pools dataset. The Place Pools dataset was constructed in the 2011 by the MIT Media Lab. So this project consists in compare two image, asking for volunteers from any part of the world, for any citizens, which place looks, in this case, livelier, or maybe safer, or more boring, more depressing, etc. So volunteers should choose between one of them or choose the option equals. So we have right, left, and equal. This dataset released two versions. The first one was released at 2013, containing about 73,000 comparisons between 4,000 images taken from two countries, USA and Austria, four cities and three main categories. The Place Pools version 2 was released in 2016 with more than 1 million comparisons, more than 100,000 images from 32 countries, 56 cities, and in 6 categories. So I will explain how we prepare the data. This is a sample of the data set. We have comparisons such as left and right image, the ID of both image. We have a winner. The result of the comparison could be equal, left or right. We have the latitude and longitude for each image. As you can see, the image were compared with different image for random cities. This project does not ensure that comparisons were made with image from the same city, country, etc. And also we have a category evaluated. So in this case, we have depressing, safety, and lively. For process these comparisons into perceptual score or rank score, we have two main algorithms. The first one, the perceptual score, is based in Sales et al., the collaborative image of the city, based in a psychological aspect. Actually, the method they use is called the strength of schedule to ponderate the lose rate and win rate, and then calculate and penalize the perceptual score. On the other hand, we have a rank score that they use to calculate the ranking of comparisons image, actually using the TrueScale algorithm developed by Microsoft. But this algorithm is used for games table board. So study the comparisons. We know that most of the image were compared about 2 times. and the comparison average is like 9. So looking for the true scale algorithm, we need a minimal of 35 comparisons per image to have a very trustful distribution. So for this, we discard the rank score because we don't have not enough comparisons for each image, and we focus in the perceptual scores. So after preprocess for each category, we have one image, one ID, and one unique score per category. So in this case, we have a church. We have 7 score in safety, high score in lively, but in depressive we have a low score. In boring also we have a low score. So in summary, we have we separate by continents: Europe, North and South America, Asia, Oceania, Africa, and count the countries and cities. Also, we have the categories, the number of comparison per category. As you can see, safety have the most number of comparisons, 300,000, and they use the all image to compare. Also, Lively use 99% of the image, but the comparisons are not the same as safety category. So in this work, we will focus in the safety category only. Let's start with the urban safety perception. So in summary, we have this number of image per continent or region: North, South America, Europe, Asia, Africa, and Australia. So this is the map of the cities. As you can see, USA has about 17 cities evaluated in this data set. Mexico has 2, Canada has 2, Brazil has 3, Chile has 2, Japan has 2 cities, and the other countries has 1 city per country. Well, then okay, let's calculate the perceptual score. For the perceptual score algorithms using the strength of a schedule, we can calculate a score, a perceptual score for each image based on these comparisons. So using filtering the image compared with other image from the same city, country, continent, and global. Global means the whole data set. We know that, for example, for the safety category, we have only 20,000 image compared with image from the same city. The same with 45,000 image compared with image in the same country, the same continent. Well, in global, we have a whole data set. In the case of boring, depressing, wealthy, we know that image compared with the same city image are less than 8% of the whole data set. So that's why we keep using the safety category, and we will use whole comparisons. We cannot study the continent, country, and city. And plotting the scores obtaining, we have this. For a city, country, and continent, we don't have a very trustful distribution of the scores. In global, we have a very meaning one. In this case, we are comparing World and Rio de Janeiro. So also we can categorize these scores using a threshold. For example, from 5 to above, we can say this is safety, and from 5 to below is not safe. We plot the imbalance of samples between positive and negative samples, in this case safe and not safe. We know that there is a city such as Belo Horizonte, Rio de Janeiro, with a high imbalance of samples in the not safe category. But also we have cities such as Atlanta, Amsterdam, Chicago, that they have a very proportional distribution with safe and not safe category. Here we compare Chicago and Rio de Janeiro, and actually, as a curiosity, we have that Rio de Janeiro have a very imbalance of samples in whole categories, excepting in depressing. We have more depressing image than not depressing image. So let's start with our experiments and results. We propose a fusion of Vision Transformer B16 model and one former segmentation model. Then we use a dense layer to build our classifier. We perform two tasks, a binary classification using 5 as threshold, dividing safe and unsafe classes, and 10 label classification. This is what we use the score. From 0 to 1 is labeled as 0, 1 to 2 is labeled as 1, and so on. We use the accuracy metric as the main metric to compare with previous works. We also perform hyperparameters tuning using grid search and stratified 5-cross validation. And whole experience we're performing using an NVIDIA GTX 1650 Ti with 8 of VRAM. For data split, we perform oversampling methods to imbalance the classes in some cities and dividing the data between 75% and 25% using the 5 stratified cross validation. So this is our one former. We start using the input image. We perform the segmentation task and we obtain the object present vectors. Also, we use the vision transformer to obtain vector probabilities. Then we concatenate and perform the classification. So in results using binary and 10-level classification, we know that our model vision transformer and one former behave better than previous one, except when we use only vision transformer. This happens in the same as 10-level classification. The vision transformer performs well, but not overpass the others, but vision transformer and one former ours overpass the previous works. For explanation, we propose that using GradCam, class activation map, so from one input, we calculate the segmentation mask of the objects. We calculate the GradCam of the model, the vision transformer. Then we perform an intersection over union to obtain labels, the intersection between objects and the class activation map with a threshold of 30% of relevance. So from this, we calculate the object relevance. So for example, for safe samples, we have an image in the left, we have a segmentation mask in the middle and cam in the right. And for this set of image, we know that the road, sidewalk, sky, and tree, they have a very high relevance in this category, the safe. And also we know that tree and sidewalk, they have a positive average impact in this category, especially tree. We also know that in these black circles that these relevance are also have a negative impact in negative samples. For example, here, unsafe samples. We have that building is a very relevant object in this category, in these samples. Also plant and person, fence, air, and cars. So we also find some limitations. The first one is the individual perception because of the volunteers were from different citizens, different countries, different backgrounds. So we found that people from Japan, the perception of unsafety is very different from people from New York. Japan prefer a quiet place as safe in the contrast with New York that they prefer a very crowded cities or streets. Also, the lack of samples. We have a very imbalance of image collected per city. Let's say Amsterdam, Bratislava, Copenhagen have less than 1,600 image. And cities such as Atlanta, Rio de Janeiro, Berlin, they have more than 3,500 image, and so on. We also find some blank non-samples from the data set. We delete that. So conclusions, we propose a methodology to analyze the place pools data set since we thought that it's better to focus on data first instead of model complexity, but we use state-of-art models. We develop a new transform-based model called urban forming. I mean, to improve the street view imagery classification applied to urban safety perception. We evaluate the importance of visual elements using the intersection over union between segmentation mask and class activation mask from the models, providing deeper insights for each category, safe and unsafe. And also we identify limitation that impacts in or analyzing generating a bias in classifying perceptions. Thanks for your attention. Please feel free to question.